What's this? Initial swallow problem. Yes, this is okay. So we mentioned the Runge-Kutter's method, and the Runge-Kutter's method is not nice because this is the this type step is actually in between the ti and ti plus one, and we use this value, the function f value evaluate at this point only one time during the algorithm. And so this is not nice. Each time you need to calculate difference f functions value, and we don't need use it anymore. And this is why the Runge-Kutter's methods have large computational cost. And now last time I give you the idea about the multi-step methods, and then the multi-step methods is to use the informations in the previous several steps. And here we are updating the I plus one nodal point value. And we use the nodal point information that is Wi minus 1, Wi minus 2, Wi minus 3. This is the fourth order Adams batch form technique. And today I'm going to also include one thing, and then that is the fourth order Adams mountains technique. And I'm going to give you the example here as well later on. This is the mountains members. MOU. To open another PDF. So sorry. Okay, this should be the mountains members. Let me just doing the things. Okay, so here the W0 is the alpha, and once again we have some information about the very first step, very first field step, and then alpha 2. And here we just need the W0, W1, W2, and which means that they are the approximations to the y evaluate at T1, y evaluate at the it could be the approximations to the y evaluated at the T1. It could be the y evaluated at the T2. And the W0 is just the initial value. And for this scheme here, we have this one is different from the first one. The first one is the Adams batch form, and this one is the Adams Moulton. And the Adams Moulton, and let's see the scheme here. We have Wi plus 1, and then Wi and plus CH, that 24, and 9 FTI plus 1, and Wi plus 1. And you will see something very weird here. FTI Wi, and then minus 5 FTI minus 1, and Wi minus 1. And there are one more term here, plus FTI minus 2, and Wi minus 2. And some students say, when they take a look at this methods or this equation formula here, and then they have questions. On the left hand side, this is Wi plus 1, and on the right hand side, we also have some things about the current steps we want to compute. And this is the Wi+1 here. And people just get confused and then know how can we do the summation or subtraction of computations on the right-hand side because we don't know this value yet. So what you do here is to write out the formula and then solve the equations for Wi+1. Does it make sense? So this is the equations about Wi+1 on the both sides. And as you can see here, for the fourth order Adams-Moulton technique, actually we just need the previous three data set data points to calculate the current step. So we are going to here, for example, here we are going to calculate Wi+1, and the informations we use from the previous stage are Wi, that is one data, Wi-1, two data, Wi-2, and this is three data. So this is the Adams-Moulton technique. So from this steps, and we don't stop here. We just go ahead, and then show the equations for the Wi+1. As you can see here, we have the left-hand side, right-hand side, both have the Wi+1 item, and then we need to solve the equations for Wi+1. And this is why, so I would like to say, if you have the Wi+1 on the right-hand side, actually people call this one as the implicit methods. Because it's not that explicit. You need to solve the equation for Wi+1. But for the Adams-Bashforth methods, and people say this is an explicit methods because you don't need to solve the equation for Wi+1. You just need to put in the values on the right-hand side, and then you get the update for the Wi+1. As you can see here, we need to solve the equation, and that's why the implicit methods, they need the Newton's methods to calculate the solution, the root of these equations. And you can use the, if you are going to use the algorithm to solve it, but I believe that for the final exams questions, you just need the solve it by hand. But people can solve their Newton's methods, solve this equation by the Newton's methods. And let's see, I should have more things about this one. So now I'm going to give you the very general idea about the multi-steps. And these are two very specific methods. Actually, you can have more general method here. And what's happening? This is the fourth orders, and then this is the fourth order Adams-Moulton. And let's see, there's some things here we need to pay attention to. And the order here, it means that this is not related to the points, how many points data we use here. Because as you can see in the fourth order Adams-Moulton, we use three previous points, and then the fourth order is Adams-Bashforth, and then we use four previous points here. Let's see, where's my pencil? Oh, it's here. So this part we have 4 points, 4 previous points informations to calculate the current point. And this one we use 3 points here. What is the meaning of the fourth order? So once again, it's about the truncation error. And this one, it means the fourth order here, it means the truncation error is the order of fourth. And then here is also the truncation error is also error is all H4. And the truncation error, once again, is to put in the true solution of the equation, and to you put in the true solution, and then replace the W here, the yi plus 1, and then replace the W with the y, and then do the subtractions, wi plus 1 minus the right hand side here, after I replace the wi with the yi, and then divided by h, and then LSC truncation error. And the truncation error here is to see how much the true solution does not satisfy the difference equation here, the difference method here. And this is the local truncation error. And as you can see here, this is the implicit methods, and then this is the explicit methods. And then for this explicit methods, and this implicit methods, they have the same truncation error, and which means that they have similar accuracy in the approximation. But here in this part, you will see we just need the 3 previous data point, and this one we need the 4 previous data point. But this one, the accuracy is come with a cost, a computational cost, because you need to use the Newton's mapper to solve the equation. And so that's why, okay, this one you use less points, but you need to compute solve the equations with the Newton's mappers. This is why we have a higher accuracy here. Actually, we need to do extra work to get this accuracy. And next, I'm going to give you the definitions of the general multi-step mappers. These are two typical multi-step mappers: the Adams-Bashforth and then the Adams-Moulton. And the general definitions of the multi-step mappers is, so this is the general definitions of it. General definitions of the multi-step mappers. And so once again, the multi-step method is solving the initial value problem. So for examples, we have the problems y prime t equals to f t y, and we have a bound for the time domain. And then we also have the initial value. And the multi-step mappers are the following. And as you can see, what we already have in the 4th orders, the Adams-Bashforth and the Adams-Moultons, the multi-step mappers is calculating the wi plus 1. Wi plus 1 is the approximation. So this one is actually the approximations of the y value at the point I plus 1, ti plus 1. And this one can be calculated. This is a general formula for it. So we have, we are using the previous, this is M step, and then we are going to use the previous M step, previous M data points here. And let's see. So we have some coefficients for it, AM minus 1, WI, and then AM minus 2, and WI minus 1. These are the previous data point. And A0, and the A0 should be the WI plus 1, and then minus M. And as you can see here, we use M data points. M previous data points. M points here. And this is why we call M points here. And this is why we call this is the M multi-steps. M steps multi-step methods. And this is the general definition. And also we have plus the H. And inside the H formula, and then we have BM and FD. This is some informations from the F function, and then TI plus 1, WI plus 1, and plus the BM minus 1, and times all this A and B are the coefficients TI, WI, and plus all the way to B0. Plus all the way to the B0 F TI plus 1. This is the F function value at the M previous data point, and also it could be the F function value at the current point as well. And so for here, this are the general formula for the multi-step mappers. The I could be the I informations here could be for I is from M minus 1, M minus 1. And as you can see here in this formula, we need the M points, the previous M points data in the algorithm. So if we want to start the algorithm, and then actually we need some informations for we need the initials with the initials value or the starting value. With the starting value, that is the very first M data points here, W0, and we let it to be the initial conditions, alpha, and W1 equals to alpha 1, and W2 equals to alpha 2, and to the W M minus 1, and these are the first very first M data points. And here I need to point out that the A1, A0, AM, A2, and then to the AM minus 1, and also the B0, B1, B2, and then to the BM are the constants. And this is the general version of the multi-step mappers. And you could have different types of the multi-step mappers. And you already saw two multi-step mapper here. They are also in the general. It's also in the general format. And we have the WI plus 1 on the left-hand side, and then on the right-hand side, we have the WI. It could be some scheme. We could have WI here, and then plus the WI minus 1, WI minus 2. But here for this Adams brush form mappers, and then we just have the WI here. But inside the parentheses, we have all the data, the F functions evaluated at the WI minus 1, WI minus 2, WI minus 3. And this is one example of the multi-step mappers. But here, this is just the general idea, the general definition of the multi-step mapper. And as you can see here on the right-hand side, we should pay attention to the right-hand side. Inside the H, the factors, it multiply it. So here, this one, as you can see here, we have the F function evaluated TI plus 1 and WI plus 1. And if the BM equals to 0, which means that we don't have distance in the formula, and we call this one as if BM equals to 0, and then we call this is and explicit mappers, because we don't need to solve the equations for the WI plus 1. And if we don't have this item, and then we just need to do the evaluations of the values on the right-hand side. But if this BM does not equal to 0, then which means that we also have WI plus 1 on the right-hand side of this formula, and we need to solve the equations for WI plus 1 and to get the values for the WI plus 1. So this one, we call it implicit method because we need to do the solving equations step. We call it implicit methods. And this is the things we have here. And when we have just one step methods, if we just have one step methods here, so if we have just one step method, and so for examples, we have WI plus 1, and then equals to the AM minus 1 WI, and then plus the H, and then BM, and the FTI plus 1 WI plus 1, and plus the BM minus 1 and FTI WI. Actually, this is one step, and then actually I can write into M equals to 1, so this one is just A0. And BM is just the B1, and then here is just the B0. And for this one, and if the BM equals to 0 here, and then we call it explicit, and then there's another name here, and then there's a special name here. Explicit, let me see, explicit Euler methods. And there's another name for it, and then because it's going to be, let me see. So for this one, it's also called backward Euler methods. Am I right here? Let me see. Yes, it should be correct. Because it's just you see informations on the right-hand side, you see things that is from the backwards directions. And this is also called backward Euler methods because if this should be the B1 equals to 0. The B1. So if the B1 equals to 0, and then we don't have this part here, and then on the right-hand side, we just look backward. And that is why we call it backward methods. And there's another name, this is explicit methods, because we just need to calculate the right-hand side items and then to get the updates for the WI plus 1. And if this one, the B1 does not equal to 0, and we call this implicit Euler's methods. And for the Euler's methods, and then you will see that we just need one step. And there's another one name for this one, and then that is the forwards Euler's methods. Because we need to look forward as well in the information. If you have B1 here, this is B1 does not equal 0. And this item is some things from the forward directions, and then this is in the future. This is the future information, WI plus 1. So we call it forward Euler as well. And this is implicit because there's another name for it is implicit because we need to solve the equation for the WI plus 1. And any question here? Because I need to make sure that you understand this part. And this is something related to your final exams, the last questions. And there's another questions here. And people just say, okay, you need the M data points to start the value, start the algorithm, and then what about this data voice? So in your final steps question or your homework questions, we use the exact values from the exact solution. So for example here, but this is not realistic. This is not what we do in practice, but this is just for your homework or final exam questions. And in your final exams questions, and we need to use the we use the exact value, and which means that for the W0 here, and then we use the alpha, and then W1, and then it just equals to YT1, and W2, and then equals to the YT2, because the two solutions is given by given in the questions. For the Wn minus 1, and then it's just the ye value at the time n minus 1. And this is the things. But actually, people is not doing this in practice. In practice, this is something people do here, and then they are using the either the Euler's methods or either the Taylor's methods or other single steps method. The Runge-Kutta method is also Runge-Kutta method to calculate the first endpoint, to compute the first endpoints, to compute the first endpoints. And this is what we did in practice, what we do in practice. Any question here? So, but for your final exams, you just need to use the exact value from the true solution, and then to start your algorithm over there. This is the things I want to mention. And let me see. I'm not going to give you the people how to divide the method here, but you can definitely go to take a look at the lecture notes I post on the Canvas. Because I want to mention one example here instead of giving you the ideas of the derivations. So for examples, for the implicit methods, implicit Euler's methods, if we want to write down the scheme, remember that the Euler's methods are just one-step methods. And then, for example, we are solving the y prime t, and then equals to the et, and then y0, and then equals to, let's say it's equals to 0.1. I'm not sure if it is correct, this problem, but let's solve it. And let's say we have the step size h, and the h is the there's a time domain here, 0 to 1. Am I right here? Not really correct. Let it to be 1. Okay, so let's say we don't know the solution, and this is the that the step size should be 0.2. Then we have the T0, T1, T2, T3, T5, T4. And what is the implicit Euler's methods? Implicit Euler's methods, that is, we actually have the things on the right hand side, and let me see. I have something wrong here. The B1 equals to 0, and the B0 equals to 1 here. And this is a combo. And this one is the B1 equals to 1, and then B0 equals to 0. And then this is the implicit Euler's methods. So here, let's say this is the implicit Euler's methods. And what we did here on the left-hand side is to apply the, actually you can apply the finite difference methods to approximate the y prime t, and you will see you will get the same things here for the methods, the formulas we derive there. Wi plus 1 and then minus wi and then divided by h, and then this is the derivative informations on the left hand side. And on the right hand side, because it's implicit methods, and then on the right hand side, actually the information for the f function is coming from the ti plus 1 step, and this would gives us wi plus 1 and then equals to wi and then plus the h e ti plus 1. And this is another way to get the formula for the implicit rulers methods. Do the finite difference wi plus 1 then minus wi divided h, and then this is the approximation for the derivative here, and right hand side informations are from ti plus 1, and I give and I do this one, and then it's equal to it's equivalent to wi plus 1 equals to wi plus these things. And if you compare this one to the things we have here, they are the same. They are the same. B1 equals to 1 here, and then B0 equals to 0. And also the A0 should be 1. So there's no A0 here, it's just 1 for this specific methods. And as you can see here, we have just ti plus 1. It's not that nice. So let me give you one more example here. You don't see anything about the wi plus 1, and then that is not so good. So let's say there's the yt on the right hand side as well. This is the fty function. And if we have one more things about that yt, and this yt, we also use the things at the time step ti plus 1, and which leads to, so on the right hand side, we have the wi plus 1 and then square. And this is the wi plus 1 and then square. Any question here? So on the right hand side, and then all the informations are coming from the ti plus 1 step. And then, so now, if you write down the equation, these are the things from the ti plus 1 step, and then we write it to wi plus 1 equals to all these things here. So here, from here, you need to solve the equations for wi plus 1. So solve the wi plus 1. And this is how we use the implicit to Euler methods. And for examples, we start from the W0, and we got W1, and it equals to the W0, and then plus W0 is just 1. And then we have the plus H, and then 0.2, and then E and Ti plus 1 is just 0.2. And then plus the wi plus 1 and then square. And from here, you need to solve the quadratic equation for the W1. Does it make sense? But I'm not going to solve these equations in the class. Any questions here? This is the implicit Euler methods. For the Adams-Moulton method, it could be more complicated. And let's see. I'm going to just show you the examples of what we have on the canvas. And there's one example on the textbook, and then this one is asking you to show the equation. Let me see. This is the Adams-Bashforth, and then the Adams-Bashforth is quite easy because you just need to substitute and plug in the values on the right hand side and then to solve it. And the difficult part is Adams-Moulton's method because you need to solve the equations for the Wi plus 1. And for this examples, we also have we use the exact values given from the YT, the functions solutions. And here, once again, we have the H equals to the 0.2, the step size. And let's take a look at the B questions. For the B questions, we use the implicit Adams-Moulton's 3-step method, and that is the same as what we call fourth order Adams-Moulton's method there. And this is the equations, the formula we have. And what about the starting point? The starting point we have, we did the W0, W1, W2, and we just plug in the functions. If you take a look at here, what we have in the W0, W1, W2, it's actually W0 is just the 0.5. And then for the W1, you plug in the 0.2 here, and then to get the exact values at the first node point. And for the W2, and then you plug in because the step size is 0.2, and for the second node point, and then that is the 0.4, and then you plug in the 0.4 there, and then you get the W1, W2. Yeah, and that is the W2. And let's see, and the next, once you get the starting point, and then you plug in the equations over here, and for with the TI information, and then it could be reduced to this equation. And we need to solve these equations for the Wi plus 1. And as you can see, this one reduced to some number here after you plug in the number into the equation. Actually, this is just a 1 Wi plus 1 equals to 1.8 divided by 24 Wi plus 1. This one is easy to solve because this is just a linear term here. There's no quadratic term here. So this one is easy to solve. Any question here for the Adams-Moulton methods? For the Adams-Moulton methods, after you write the formula, and then actually you need to solve for the Wi plus 1 because it's implicit. And people love to do, some people just say, okay, explicit method is super easy. We just need to plug in the value. Why don't we just use the explicit methods? And there's one downside for this, for the explicit methods. That is because the explicit methods, actually, there's some requirements for the, so for the step size H, and then it's smaller than or equals to a specific number. And then this specific number and is defined by the this specific number is related to the equations, and the step size could be very small. And so when you are doing some questions and then with a larger step size, and then this one, the explicit methods does not work. But for the implicit methods, the implicit methods is good, and then that's because there's no restrictions on the step size. On the step size H. And this is the pros for this one. And this is the cons for this one. And what's the pros for the explicit methods? The pros methods is easy to compute. But the cons for this one, more computational cost here, more cost here, because we need to solve equations. And these are the comparisons between the explicit method and the implicit methods. And I believe that is all the things we need to talk about in this quarter. And I'm going to hold office hour Thursday on Thursday. And on Friday, I will stay in there. Let me see. I promised somebody to do some extra things. Let me see. On Friday, maybe we just cancel the class. Because maybe you don't have any questions by so far. Let me just hold the usual office hours on Tuesday. Next Tuesday. If you have any questions, and then you can go to my office hour on Tuesday, next Tuesday. And I just cancel the Friday one because maybe you need some time to come up with some questions. And if you find any typos on the final steps, then please email me as soon as possible. And if you have any question about their exams as well, maybe this question is not correct. Maybe you are composing wrong questions on the final exam, and then let me know. But you cannot ask me how to do this. I don't know how to do this question, and this is not permitted. And so this is all the things. And nice to see you this quarter, and then hopefully I can see you somewhere elsewhere, maybe in another university, in the canteen. I know some of you are going to another university for master degree, so see you there. I will go to the dining hall to see you.